to show you how you will be recording your answers on the test. You're not just going to put DNE, but you have to show us all the steps, and I'm going to be taking you through a step-by-step process. Okay, so for the very first example, now in the place of multiple choice on the upcoming test, we're going to give you something just as or even simpler than multiple choice for some easy marks, and that will be pictures of graphs. Now this is a piecewise function graph. The whole thing represents g of x. There will be situations where you will have color-coded graphs. Some of them are will be f of x, some of them will be g of x or h of x. But multiple graphs where you have to examine the limit. Now, here we are looking at one-sided limits. You will see from that little negative sign for the first one. So if I put limit of g of x as x approaches 2 from the left. So I'm approaching 2 from the left. And remember, we discussed yesterday that our limit is the intended height of a function. So I'm really approaching the intended height, the y value of 3, when I'm approaching 2 from the left. And that is how I find the limit. So you see how simple that is. You're going to get marks. We're just identifying limits. So in Mr. Bullock's opinion and my opinion, we think that is some very easy marks that would replace the multiple choice component on this test. Now, if we look at the next question, and we approach g of x when x is equal to 2, we're going to be approaching this time from the right. You can see, because this is not a continuous function, we are going to get a very different intended height of the function. Here we have the limit is equal to 1. Now, the key component here and our definition of the limit that we learned last time, because the left-hand side as x approaches 2 and the right-hand side of the limit as x approaches 2 are not the same value, we have to say that the limit of g of x when x approaches 2 does not exist. Now, this does not mean that for other x values on the graph, the limit is not going to exist. That is not the case, just when x is approaching 2. If we scroll down a little bit more, and I'm going to erase what I did previously, now we're going to look what happens when x approaches 5. So you can see as I'm approaching 5 from the left, I am, even though the function is not defined on that particular curve, when x is equal to 5, that's why we have the open circle here, as we are approaching 5 from the left, it is clear that the intended height of the function is equal to 2. Now, when we are approaching from the right, despite that removable discontinuity, we are also approaching 2. So despite the fact that f of x is defined at a completely different value, f of 5 is actually equal to 1, and that is not easy to see, so let me erase that. Even though that is the case, because the function as we approach 5 from the left-hand side and the right-hand side, the limit is equal to the same value. That means the limit of the function as x approaches 5 is 2. Okay, let's move to another example. So here we have two different graphs, the f of x graph and a g of x graph. The f of x graph is in purple and the g of x graph is in blue. When you're doing these questions, you have to be very careful, because even myself, when I was teaching this morning's class, I automatically was attracted to the purple graph, and I had to remind myself, well, that's f of x, not g of x. So the first question is asking, when x is equal to -2, what is the value of f of x? Now at -2, you can see there's an open circle at y is equal to 1, but there is a closed circle at +2. So we're not talking about limits yet, but the value of that particular function, f of -2, is equal to 2. Now, when we are approaching +1, this time we're talking about the g of x function. So that is the blue graph. So when we are approaching 1 from the left, you can see that we are approaching an intended height of -2. So the limit of the function as we approach from the left is -2. Notice that g of 1, when we plug x is equal to +1, into the equation, we also get -2. But more importantly, when we are approaching 1 from the right, we don't get that same intended height. This time, the limit of the function from the right is -1. So because the limit from the left is different from the limit on the right, that means that the limit of g of x when x approaches 1 does not exist, DNE. But we can say that as the limit as x approaches 1 of f of x, and we're just going to go up quickly. Oh, didn't want to do that. Okay, we're going to go up quickly. And that same x term, when I'm approaching from the left, I get an intended height of +2. When I'm approaching from the right, also an intended height of +2. So the limit of the f of x function as we approach 1 from the left and the right is equal to 2. So hopefully that clears up any misconceptions you might have and gives you an idea of what you will be doing with graphs on the test. Now, here we have another piecewise function. And we are going to determine, as x approaches -1, the limit of the function f of x, this entire piecewise function, as x approaches -1. And we're also going to figure out the limit of the function as x approaches +1. Now, to make things easier to read, I'm going to graph this function. The top line is going to be, oh gosh, sorry, let's admit the student. Andrew, Mr. Bullock has entered. Okay, so the very top part of the piecewise function, when x is less than or equal to -1, will be in red. In between -1 and +1, it will be blue. And when x is greater than and equal to +1, it will be purple. So the graph looks something like this. Okay. So right now, and so you can see that we have two linear functions and a bit of a quadratic function. Now, the purpose of this example is to show you good notation. So please be clear, if your notation isn't correct on the test, you will lose some marks for that. So your notation is very important here. And we're going to start off with examining, so we're not looking at the different equations, but I want to examine what happens. And I have misplaced my stylus. Where did it go? Oh, there it is. So I'm going to erase what's already on the screen. And we are looking at the function, the limit, when x is approaching -1. So I don't need to worry about my purple graph at all. I just need to worry about two equations. The get this out of the way. And I want to erase this a little bit. Okay, so the first equation is negative x minus 2. That is my red graph. And as I'm approaching from the left, negative x minus 2 is approaching negative 1. My second graph is the function x. So you can see that as we are approaching negative 1 from the right, we're dealing with this function, and that is also, that has a, sorry, oh, no, I should be going like this. There we go. That's easier. Okay, so I'm approaching negative 1 from the right of x, and that value is also equal to negative 1. So because as I'm approaching from the left and as I'm approaching from the right, the intended height of the function is both negative 1. That means the limit of the function as x approaches negative 1 does in fact exist and is equal to negative 1. So this is proper notation. Now I'm going to erase this. And this time we are looking at what happens as x approaches positive 1, which is what confused me because I need to get rid of the graph like this. So as x is approaching positive 1 from the left, I have my blue graph over here, and we are reaching an intended height of y is equal to positive 1. However, as I approach x from the right, I need to follow this purple curve, and that graph is reaching an intended height of negative 1. So because these values are not the same, now it's not only because there is a jump discontinuity here, it is possible for the limit to exist when the graph is not continuous. But in this particular example, these values are not the same, so we say that the limit of the function f of x when x approaches 1, if you don't tell me what the number is approaching, then your notation is not correct. But at this particular value of x, the limit does not exist of the function. Okay, so let's look at another example. So this is very straightforward. It's another piecewise function. All of this is f of x. I've highlighted something in the corner. This is something I want you to review on your own, but I want to point out two items. First of all, we can take the limit of the same function at different values of x. That's something you should notice. But also notice what happens near this asymptote, near this red asymptote over here. So as x is approaching positive 5 from the right, my graph is going to, the whole idea of an asymptote is the graph is going to get closer and closer and closer to positive 5, right? But it is not going to stop. It's going to continue to go infinitely, go to very small decimal places. So how we say that in mathematics is that as x approaches 5 from the right, the limit of the graph is approaching negative infinity. So it's going to keep on going and going and going. Now, something else. So this is a good practice question for the graph. We don't have any positive or negative infinity otherwise, but I can pinpoint, let's see, number C over here. So when x is equal to positive 1, similar to other questions we have done, from the left, we are approaching a y value of 3, but from the right, we are approaching a y value of 1. So that's why the limit does not exist. If you have questions on anything on this slide as you're reviewing your PDFs, please ask Mr. Bullock and myself to review it with you. but very straightforward. So at this point, we are going to start talking about continuity. So a function is continuous if the graph of the function contains no breaks or holes. That is the definition of continuity. You will notice for the example on the left, even though there is a removable discontinuity here, as we are approaching from the left and that discontinuity, and as we're approaching from the right, the limit of the function has the same value. So even though x is equal to 2, f of 2 is undefined, and the function is discontinuous at x is equal to 2, the limit still exists. Now, this is different from the example on the right, which is an example of an instantaneous change in value. Here we have different values because of all those jump discontinuities. So even though the function is defined at, for example, f of 1, it is discontinuous for so many other values. And the limit, nothing is approaching from the left or the right. So that brings us to this definition. And this is something you have to memorize. The function f of x is continuous at x is equal to a if it is defined and the limit is defined. That means the limit from the left is equal to the limit from the right. And f of x has to be equal, the limit as x approaches a has to be equal to f of a. These are two elements to define continuity. If either of those elements are not true, then the function is discontinuous at x is equal to a. So this is something to keep in mind when you're doing your homework. We're going to talk right now about different forms of discontinuities. So the first one is a removable discontinuity, which you learned in MCR when you're canceling from the numerator and the denominator and you have what you would call before a restriction. That is really a point in the function that makes it discontinuous, and it creates a hole in the graph of the function like you would see right here. This is called a removable discontinuity. A jump discontinuity often occurs in piecewise functions at values of x where the one-sided limits are not equal. So right here we have the graph breaks off into a jump discontinuity and jumps from y is equal to 2 to y is equal to negative 2 and starts off again. So even though it's defined at f of negative 2, there is a jump discontinuity here. And finally, infinite discontinuities occur when there is a vertical asymptote. You had lots of practice of that with asymptotes in general in MCR as well as MHF. Endpoint discontinuities occur when only one of the one-sided limits exists, which often happens in radical functions. So to summarize, we have removable discontinuities, jump discontinuities, and vertical asymptotes or infinite discontinuities. Okay, so again, I'm going to show you proper notation. So I'll use my screen here. So we're going to look at the equation and the function. Here I have a quadratic equation in the purple graph when x is less than 1. When x is defined is in between but equal to -1 and +1. You can see right here between -1 and +1, we have a horizontal line defined as y is equal to 0. And then from when x is greater than 1 onward, we have another quadratic function. So how are we going to analyze these limits? Well, first of all, we're going to talk about the function as when x is approaching 1, positive 1. Let's see, I meant to write negative 1. Please fix that in your notes. Negative 1. Negative 1 from, and I think I should make that a little bit neater. Okay, so as x approaches negative 1 from the left, so as x is approaching negative 1 from the left, let's highlight it on the graph. As we are approaching, we're getting to the intended height of 2, following along the purple curve, because that is the only part of the function that extends when x is less than negative 1. So we have to follow that. When we get to negative 1 from the right, there's only one option for the function. That is the function y is equal to 0, and obviously the value of that function is equal to 0. So at negative 1, the function is not, the limit, is not the same as we approach from the left and as we approach from the right. Therefore, the limit does not exist. Not get more clear than that. But now we have to move on. We have to find out the behavior of this function at other points in the graph. So we're going to talk about as we are approaching positive 1 from the left and as we are approaching positive 1 from the right. So let's erase anything that I had previously done. Okay, so when I'm approaching positive 1 from the left, I find myself on this horizontal line, y is equal to 0. So the value of the function is equal to 0. However, when I'm approaching from the right, I'm on my red quadratic function. However, as I approach x is equal to positive 1, I find myself back at an intended height of 0. So that means the function at x is equal to 1 is approaching 0 from the left and the right. And on top of that, f of 1, so when we plug x is equal to 1 into the function, we find that it does have a value of 0. All of these numbers or these solutions align. So the limit does exist at x is equal to 1, even though the function is discontinuous at x is equal to negative 1. So please, I've had students before just look at the function, oh, it's discontinuous. That means, there are no limits that exist. That is not the case. Please don't confuse that. Now, the next example I've included in the notes. I want you to try that on your own and compare yourself with the situation, compare your solutions or how you would write the solutions with how I have written the solutions in my notes. We already know as we're approaching from the left and we're approaching from the right, we've had many examples like this. So we know that the limit exists, but I want you to practice how you write the fact that the limit exists and how you express the removable discontinuity. So please keep that in mind and attempt this question before looking at my solutions. Okay. So now we are going to talk about different methods for evaluating limits. This is essentially the toolkit. When you ask us what is going to be on the test, well, this is what's going to be on the test. Looking at graphs and then evaluating limits using various tools that you have collected along the way. So just like I told you the other day, grade 9, grade 10, grade 11 math is all part of a language that we use, the alphabet of mathematics. And without learning the alphabet, we cannot speak this language of calculus that I like so much. So for polynomials, we often use substitution as a method. Mr. Bullock and I are checking right now in the questions that we've developed, and we're going to make it quite clear. When you are not allowed to use substitution, we will say use first principles, for example. And when you are allowed to use substitution, that will be clear too. A point for both you and myself, Mr. Bullock. So we cannot use substitution for rational expression when we use substitution and get something like 0, 0, which we've talked about. That is called the indeterminate form. And I've written a note here, if you get an indeterminate form, you must manipulate the expression to a form that allows you to evaluate by substitution. So methods of achieving this. So if you look at this list and think, oh, I really hated that before, you've got to get better at it in order to do well in calculus, because it's going to come up over and over. The skills of factoring, the rationalizing skills. Sorry. Here we go. Expanding and simplifying, common denominators, rationalizing denominators, change of variable. I'm going to do some examples today and a lot more examples tomorrow. So the first thing, examples of indeterminate limits. When you try to factor these particular equations, direct substitution is going to lead to a 0, 0 situation. This tells us, so if we ask on the test, what does indeterminate form tell us? Well, it tells us the function is not continuous. As a result, we must manipulate each expression into a continuous function before we can evaluate them by substitution. And we're going to do some examples over the next couple of pages. So I'm going to start off with examples where you can use substitution. Obviously, you have to clear the graph and be able to picture it to know that there is no discontinuities in the graph. So quadratic functions are a great place to start. Quadratic functions don't have discontinuities because there are no denominators or restrictions. So x squared plus 2x minus 3 is a very straightforward parabola. We know the function is going to be continuous, so we can simply plug in 5 into the equation where we see an x and get a value. Now, if I were to ask you to solve this using first principles that we learned about yesterday, then you would have to calculate and show me. So f of 5 plus h minus f of 5 all over h. That was first principles. So please don't rush through your test and say, oh, I can solve that through substitution, when the question is asking you to solve using first principles. Maybe Mr. Bullock, can you please take a look and remind, we can talk about after class if there are first principles or if we need to add them tonight. I can't remember right now. Now, this is a situation where we have x plus 2, we have a restriction that x cannot be equal to -2, but where the limit we're asked to find has nothing to do with -2. It's when the behavior of the graph as x approaches -1. So I would visualize this first on a graphing calculator, make sure the function is continuous, and then use direct substitution unless I was asked to solve using first principles. The same thing for this rational function. We can use direct substitution for this particular example and get the key thing is that if you are able to use first principles and use direct substitution and get the same answer, then you know that the function works and is continuous. Now, something we have to be aware of for a question like this, we can't just use direct substitution. We need to factor. You need to factor when you're able to factor. The numerator is a difference of square situation. So if I didn't factor it, I would be unaware of this removable discontinuity that would happen if I take 3 plus x, set it equal to 0. That means there is a removable discontinuity at x is equal to -3, which you would be unaware of if you did not factor the numerator. And I want you to try graphing all of these functions and visualizing to make sure, now that I've showed you lots of examples with graphs, that you can visualize what the limit means. Now for this original function, we have the limit as x approaches 0 of 1 plus x minus 1 over x. Now this section in red over here, remember that that is called the conjugate. We have to multiply by the conjugate, even if it's in the numerator. When it's not in the denominator, we still have to multiply by the conjugate in order to fully simplify and solve this equation. When we multiply by the conjugate, you will notice that the numerator cancels out. The 1 plus x and the minus 1 cancel out. So I'm left with an x by itself in the numerator. I have a complicated denominator, but what happens by leaving the denominator in factored form, the x in the numerator cancels out with the x in the denominator. And I'm not going to be worried about my complicated denominator because at this point, once I'm completely simplified in simplified form, I'm going to highlight that. At this point, I can simply substitute 0 in for x. So wherever you see an x into the equation, I'm substituting 0 and I get a value for that limit. So please don't be worried when you see radicals. Radicals are doable. The test is not going to be full of radicals, but you might have 1 or 2 questions on the test that have them, and you need to be able to work with radicals, conjugates, rationalizing denominators, which were multiple units in the MCR course before we went on lockdown. So if you were a student who only did 2 or 3 MCR course units last year and still got the credit, obviously you're going to have a lot more difficulty than students who did the entire course. That was a choice that was made, and there are ramifications to our choices. To be able to do well in calculus, I cannot teach you guys how to factor. There's no time to teach you how to rationalize the denominator. We have to, Mr. Bullock and myself, have to depend on your prerequisite skills. Often a mistake I see on tests is when students say c 2 plus h squared, they're forgetting that that means 2 plus h times 2 plus h. And I've highlighted over here that you have to expand using FOIL. There's a reason in MCR we drilled lots and lots of questions about FOIL and expansion, because that is key to grade 12 math. Once we have simplified this, and so this is method 1 on the left-hand side. We can simplify this function. You can see the h in the denominator cancels with the h in the numerator. So we simply have 4 plus h. And instead of the h, you can substitute 0 to find the value of that limit. Another strategy, because algebra has multiple strategies, a harder strategy I would think would be factoring using difference of squares and eliminating from there, but that does also give you the same answer, and it is correct. It's probably not a strategy I would use, but it is possible. Okay. So I wanted to kind of walk you through this. So let me erase what I did with the last class. This is also called a conjugate radical, a question that requires a conjugate radical. But before that, I'm going to explain how you can take a complex question and rewrite it a little bit. So instead of the yellow portion, 1 over root x minus 1, first of all, I have to change it into a common denominator, which would be 1 over root x minus root x over root x. So this portion, oops, I'm going to highlight in yellow. This portion is actually the entire numerator. Now, instead of saying divided by x minus 1, well, that is the same as saying multiplied by 1 over x minus 1. So written this way, the question is a lot more easy to tackle. So you can take difficult questions and you can rewrite them to make it easier to deal with. So when we multiply all of this together combined, we get 1 minus root x times root x times x minus 1. It is clear that the conjugate in this case is the opposite of 1 minus root x. 1 plus root x over 1 plus root x. You are going to have to practice using conjugate radicals and rationalizing the numerator and denominator. If you skip those concepts in MCR, it will affect you on this test. So you simplify and evaluate, and very straightforward from there, but I just wanted to walk you through that difficult question. Now, kids, please, we're limited to what we can do. So when you say, I don't understand the conjugate, it's not something that Mr. Bullock and I can fix. We always also depend on you to take the initiative to watch YouTube videos, read in your textbook, because that is an MCR skill, and we are expecting you to come into this course with MCR skills, as would any calculus teacher in the entire board. And so my advice to you is take it step by step and watch lots of videos on conjugate radicals if this is a concept that's difficult to you. Now, I've included this question for you to look at. Obviously, you can solve this question the way it is with a power in it. I don't think I put anything like this on the test, but there might be questions like this in the unit guide where it is possible to say, you know what, this is really tricky for me to tackle. I don't like fractions in the powers, so I'm going to replace let a be equal to x to the power of 1 over 3. And you can modify your whole equation by replacing it with a, and then you can factor that back in. So because your answer is 27 and a to the power of 3 is equal to 27, you can then figure out and solve what you need to solve later on. This is just a strategy that can be used to solve difficult questions, but I don't think there's anything like this in your unit guide. I just, this is in my normal calculus lesson, so I just put it in case it might be helpful to you. Now, I do want to talk about factoring polynomials. Mr. Bullock, now I know when Mr. Kushiri asked me last year, why didn't we do derivatives at the beginning? Now I have an answer for that. We cannot do derivatives usually when we're in a traditional Mary Ward. We start off with the hardest concept called vectors, which is actually a concept we've cut out of this course. But the reason we do that is we'll try to align functions in calculus together. Now, in a quadmester system, unless you've taken functions before, that's just not possible. That is why I've included the MHF playlist of all my seminars, because we teach in MHF how to factor polynomials. My MHF kids will remember this. Our synthetic division, this is called synthetic division or long division, can be used to simply factor complicated variables. In my YouTube video, I walk people through this step by step. But kids, when you tell us, well, I don't know how to factor this polynomial equation, it is a skill for calculus. That's why MHF is a co-requisite. So we are giving you that resource, that YouTube channel, to help you develop that skill. Kids who did it in the summer and last quad, they'll know how to factor a lot better. But on the test, we are not going to include so many complicated polynomial equations, but it is a skill you're required to know. And I believe it's the first unit in function, so you should be learning it right now, depending on how Mr. Kushiri has planned out his course. That's how Mr. Bullock and I taught it. So yeah, I just wanted to include a slide with the name of the strategy, synthetic division or long division. And this is an actual question from your unit guide that I just wanted to point out. This was a question you have to use first principle to solve. So determine the slope of the tangent to the curve y is equal to 1 over x plus 2 at x is equal to 3. So the way the solution is presented, we have to first figure out what f of 3 plus h is and subtract that from f of 3 from that. So if I plug in x is equal to 3 into this function, 3 plus h, sorry, into this function, I'm going to get 1 over 5 plus h, 1 over 5 plus h. Now, I can kind of get rid of this divided by h by writing here that I'm going to take the limit of the function as h approaches 0 and multiply everything by 1 over h. Now, when we subtract 1 over 5 plus h minus 1 over 5, I need to come up with a common denominator. The only common denominator is 5 times 5 plus h. So you will see that the numerator does not have a 5, so that's how the numerator becomes 5. This denominator does not have 5 plus h, so we have to write the 5 plus h in the numerator. So it's quite simple to simplify the numerators. But you will see that the answer in the book is wrong, and that's why I've included in an appendix under important tools that gives you corrections to the answer key, because the answer key says negative 1 over 10, but it should be, when you plug in 0 into this equation, 5 plus 0 is 5. 5 times 5 is 25, so it should be a negative 1 over 25. So I've just worked through the solution because I think the answer in the textbook is not written correctly. And that brings me to the end of the lesson. I just want to point out a page in your unit guide that looks like this. It was taking the derivative of the function, the cubed root of x. Now, if you use Desmos to graph the cubed root of x, as I believe we were approaching 0. So as we're approaching 0, you'll see that the tangent line actually becomes y is equal to 0, a vertical line that has an undefined slope. Any vertical line has an undefined slope. So the limit doesn't actually, well, sorry, what does it say here? There is no derivative at x is equal to 0. So when we're taking the limit, this question can be quite complicated because you have to take the conjugate of the numerator, and then some people, there's different strategies. You can convert it to exponents. But a question like this, because it freaked out a few of my kids in the last class, would be very difficult. There's lots and lots of steps. I don't think we have anything like that on the test. So though it's important to practice conjugate radicals, it's not going to be, something like this is not going to be a huge part of the test. So